We will get started. Howdy all, my name is Dr. Rob Hartz. I am the Deputy Director of the GMU Observatory, which is about 4 stories right above our head. And so I would like to give you an introduction to our program here at the Observatory. Assuming that'll work. So we are in what I am calling the Observatory Tower, and hopefully the university will at least pick up on that at some point, because we are a nice silver tower. The observatory is on the top of it. The arrow is pointing to the control room. The one silver lining of the pandemic was that it accelerated one of the things that we wanted to do anyway, which is make our telescope remote. That is common practice among research-grade telescopes. Sadly, because that means that I probably will never be able to go to Hawaii. But what this means for our telescope is that our students can actually access our telescope with the proper credentials anywhere there's an internet access. Actually, Jonathan fixed one of the problems with the telescope sitting right over there. Our telescope is used primarily for educational purposes, but it also is obviously for public outreach and research. We do exoplanet follow-up here. If you are a student or know a student here, you can join photo, which I'll put up in a moment. And students have, I wouldn't say unfettered access, but pretty significant access to our telescope. Those pictures that you see around, those are pictures taken solely by students. What they do is they take pictures in a blue filter, a green filter, a red filter, and combine them to make those color images. And they're getting better at it. So the one on the left is the Cocoon Nebula, and the one on the right, which is not quite done, they're still collecting data on it, has a very sexy name of IC number plate. I don't remember what numbers that is, but these are two of our attempts at a deep sky image, which is the image, the same part of the sky for hours rather than minutes. This, of course, is Evening Under the Stars, which is a public series that we do this 5 times a semester, obviously now. The remainder of the dates are located up here. We have, the reason why you might want to come back is, well, 1, the weather right now is not great, and 2, we have different speakers every event. Right now we have Dr. Erika Hamden. Next week we'll have Dr. Josh Pepper, who will talk probably about exoplanets, because that is kind of what he does. Today we'll have a talk for about 30-45 minutes, then a brief Q&A, and then we will take you up on the roof to tour our observatory. As I said, unfortunately it is clouded over, so all that we can do is show you the instrument and tell you more about our observatory. This is not a one-person operation. As I said, I'm the Deputy Director. Dr. Peter Plavchan is the Director, and we are assisted by 2 graduate assistants, Kevin Collins and Emthanya Pong. And we also have, Jonathan's up there twice. That is Jonathan. Jonathan's up there twice because he is not only one of our tour guides, but he's also the president of the Friends of the Observatory student organization, which is very quickly taking over campus. I think have we beat Culinary Club yet?
Yeah, far in between.
Oh yeah, so we demolished the Culinary Club. Awesome. I think D&D is next, or anyway, so we also have this here is another one of our tour guides, and Aiden, who is on the roof, is who you see when you go up the roof, is also another one of our tour guides. If you're interested in becoming a member of Friends of the Observatory, here is a code that you can QR code. If you're interested in what we are doing here at the observatory in both our public outreach efforts, our educational efforts, and our research efforts, I would suggest that you subscribe to The Moon, the Mason Observatory Outreach Newsletter, which we hope to put out once every month. And it also will have fun things like the constellation, talk about our constellation a month. I will have some kind of space news in there and so forth. One of the things that I've been here for about 3 years, one of the reasons why I was brought in and specifically told the university when I was trying to take this job is I want to greatly improve the public outreach. That does not only mean events here like here on campus, but also events off campus. We have an inflatable planetarium that we try to take to elementary schools or secondary schools as often as we can. We also have telescopes that we want to take out and have nighttime activities with them as well. That unfortunately will require some funding. So if you're interested in helping us achieve those goals and expand outward, I would suggest you become a patron of the observatory. And if you look at the bottom, there is my name, so I put my money where my mouth is. But without further ado, we have Dr. Erika Hamden, who I discovered on actually Instagram, where she does some fabulous short form astronomy education. Basically, she answers certain questions like, what are gravity waves? What is the best vacuum in space? Is the Earth flat? It's not, but I can attest personally that there are too many people who still think it is flat. She is a professor of astrophysics at the University of Arizona. She specializes in building telescopes. I informed her that I believe she is the first instrumentalist that we have to give a talk, so I'm very excited about that. Also, she observes in a wavelength that you cannot observe from the ground, ultraviolet. Because we don't want to, thankfully, the atmosphere blocks most UV light, because if it didn't, we'd all get cancer and die. But for astronomers like her, she's very much limited in that she has to go into the stratosphere or space in order to get any kind of data whatsoever. And even the data that she probably gets, she probably what we call photon limited, but going off on a tangent. She's a leader in the field of space astrophysics and has developed programs to teach early career scientists how to develop their own space missions. She is the deputy principal director of Astronomy, a NASA orbiting telescope, which is in development. She's a former chef, which I did not know and am very intrigued by. A TED fellow, a AAS if-then ambassador, an aspiring astronaut. So if you have any questions about how to become an astronaut, she probably can answer those. And she's currently working on her pilot's license, and I think she's also a power lifter. If I'm correct with one of the pictures that I saw on Instagram recently. So again, without further ado, she's going to be talking about, the title of her talk is Observing the Universe in the Ultraviolet. So without further ado, Sharon.
All right. Well, thank you for that lovely introduction. I need to edit my bio because I got my pilot's license in December of last year. So
I thought so.
An actual pilot. Okay, so I'm gonna just share my screen. And I'm really excited to talk to you guys today about the universe in the ultraviolet. A lot of people don't think that much about other ways of looking at the universe, but we actually have like this really wide range of wavelengths of different types of light that we can investigate, and they tell us different things about all of the objects in the universe. So the first thing is, what is the ultraviolet? So when we like observe the world with our eyes or with telescopes on the ground, we're looking at a very narrow slice of all photons that are out in the universe. We're looking at just this little range here called visible. So this is a plot showing the entire, what we call the electromagnetic spectrum. So it's all types of photons. They have different wavelengths. So I won't get into this, but you can follow my Instagram. Maybe I'll talk about it. Photons. Light is both a particle and a wave. So for certain things, we like to characterize it as a particle. Other things we talk about its wave properties. It's actually both at the same time. That's like a weird property of quantum mechanics. But so the wavelengths of visible light are on the order of hundreds of nanometers. So a nanometer is 1/1000th of a meter. It's a teeny tiny length. And actually our eyes evolved to observe this particular wavelength because that's where the sun peaks in its energy output, which I'll show in a little bit. But we have other wavelength types which have different properties. They have more energy or less energy. So infrared photons, if you've ever used a thermal camera, you're actually looking at infrared photons. Those have less energy, a longer wavelength. And then you have microwaves and radio waves. Radio waves are a type of photon. It's not sound. And then if you go in the other direction towards shorter wavelengths and more energy, you have the ultraviolet, and then X-rays and gamma rays. And X-rays and gamma rays are more energetic than the ultraviolet. And the ultraviolet, actually, for activities on the Earth, we actually split it up into these categories: UVA, UVB, and UVC, which are sometimes used to designate types of sunscreen. And the reason is because most of UVC light, for example, is blocked by the atmosphere, but UVA light is actually can get through the atmosphere. So certain sunscreens you need, depending on where you are, like what altitude you're at, you might need better coverage. But as Dr. Parks said, UV astronomy is really hard because the photons actually don't get down to the ground; they get blocked by the atmosphere, and that's really important for us because UV photons, similar to X-ray photons and gamma ray photons, they can be ionizing, which means that they can like knock out electrons or particles in your DNA, or in the instance of UV light, most of it would get absorbed like just in the surface of your skin, which is what's shown here on the left. And that can cause damage to the cells, which can eventually cause skin cancer. So UV light being blocked by the atmosphere is really good for us as humans, but it's annoying for UV astronomy. And then this figure on the right is showing the basically the output of the sun. So how much energy the sun is putting out versus wavelength. And so the visible band is this little narrow part right here, but you can see that that perfectly matches up with where it peaks. The sun puts out most of its energy in the visible. Our eyes are evolved to observe where there's most of that that information. And then the UV, it starts to drop pretty significantly. So this figure is the axes are what's called a log scale. So instead of the numbers incrementing like 1, 2, 3, 4, 5, it's 1 and then 10 and then 100 and then 1,000. So small differences in this scale are actually quite huge in kind of a normal life. So the sun doesn't emit too much in the UV, but it emits enough that it would be a problem for us if we didn't have the atmosphere. And so because of this, the best place for UV observations is as far above that atmosphere as you can possibly get. And that's as you sort of move higher and higher up into the atmosphere, you get access to other to parts of the UV. So some of these UVA rays, the ones that are closest to the visible, will actually make it down into, you know, the part of the atmosphere where like planes are flying. If you have a telescope on a really high mountain, like in Hawaii or the Canary Islands, you might be able to observe down into the UVA band. For things like the UVB band, they're mostly blocked by the ozone layer. So you have to be somewhere above that, getting closer to the top of the stratosphere or then into the mesosphere. And then for the very extreme UV, most of those are blocked by like the very high part of the atmosphere. So you have to be a lot higher. So most UV telescopes are going to be in space or they'll be in the stratosphere. This figure here is just showing some of the other wavelengths, because certain other parts of the electromagnetic spectrum also you can't observe from the ground. So for example, X-rays and gamma rays are completely blocked by the atmosphere, which is very good for us. They're also they can be really damaging. That's why you shouldn't get an X-ray every single day. And then even parts of the infrared. So part of the reason why we have telescopes like JWST in space is because we can't access those wavelengths from the ground. And this atmospheric transmission, this is kind of a nerdy slide, but I just think it's like fun to know about why this transmission is so variable over the course of the kind of set of wavelengths. And it's interesting because in the infrared, most of it is due to water vapor. Water vapor in the atmosphere will absorb infrared photons really efficiently. But for the ultraviolet, so that's what this blue line, this blue area is here, and that's mostly dealing with infrared photons. The visible is basically transparent. So if we look at all these different components, they almost don't really do any absorption. There's a little bit of absorption from Rayleigh scattering, which is part of why the sky is blue. And then the UV, it's really just getting absorbed by oxygen in the atmosphere, and then ozone, which is three oxygen atoms bonded together. So oxygen molecules of different types are what are doing this observation. So if there was a planet that had life that didn't rely on oxygen and there was no oxygen in the atmosphere, then they could do UV astronomy from the ground, which would be pretty weird. And if you are like, one thing that can be challenging if you're doing infrared astronomy is if you notice the water vapor lines create these kind of troughs where there's parts of the atmosphere that you can observe really easily in, and then other parts where you can't. And so infrared astronomers have to deal with like all these little broken up band passes when they're doing their observations. So my work is mostly focused on putting telescopes above the atmosphere and trying to observe the universe using those telescopes. And I, just for like a fun little historical thing, the actual very first instance that somebody at least published this idea of like, hey, we should put a telescope into space, was in the 1940s. It was this professor who, at the time, he was a professor at Yale. His name was Lyman Spitzer. And he wrote this little paper that was like, hey, I think it'd be cool to use rockets to put a small mass that had scientific equipment on it as an artificial satellite. And this is 1946. This is before Sputnik. This is before the space program. Rockets had been used in war, but not necessarily like put things into space. So this is kind of like a really big, I think like a big forward leap. This kind of instrument that he's suggesting basically turned into the Hubble Space Telescope. So he writes up later on about how it would be really interesting to put a large reflecting telescope many feet in diameter above the atmosphere of the Earth. So this is the beginning of the Hubble Space Telescope. Of course, it didn't get launched until the 90s, so it took like 44 years after he wrote this first paper before it finally happened. And there's a few reasons why you might want to put a telescope into space beyond just those wavelengths, the wavelength coverage that I talked about. A ground-based telescope has to look through the atmosphere. It's this big ocean of air between us and the targets that you're looking at. So the atmosphere basically will cause your images to get blurred a little bit. It's the exact same effect that causes stars to twinkle. It's like little, as the light is moving through the atmosphere, it gets deflected by little bits of basically the atmosphere acting like a lens and like moving things around. So if you compare an 8-meter telescope, which is a huge, that's the diameter of the primary mirror, to the 8-meter telescope on the ground, to the Hubble Space Telescope in space, even though it's smaller, has less collecting area, you get much higher resolution images. So this is the same galaxy in both the top and the bottom. And the ground-based giant telescope, still the galaxy looks like a blur, whereas here you can see some of the structure. You can see it's like sort of this interesting spiral, all this stuff that you can't actually pick out from the ground-based image. And this is also true for at infrared wavelength. So the JWST image, this is one of the very first images. I like love this image. This was the first image that they put out, and it's part of the alignment of the telescope. So this was happening in 2022. And they're mostly showing this image just to show like, oh, how good is this star spot in the middle right here? But actually the thing that I think is the coolest is all these galaxies that are on the side all over the place. Like there's just galaxies everywhere. But you can just take one of these galaxies, not even from a science image, and compare it to a ground-based telescope. And the improvement in resolution is just so incredible. And that comes partly from having a big telescope, but also because the telescope's in space. I mean, this blob here, you can't even tell that it's two galaxies, whereas the JWST gives you that really sharp, perfect focus. So telescopes in space are great, both from a resolution standpoint and from a wavelength coverage standpoint. And one of my, like the axes that I grind in my professional time is that I feel like the UV is this completely undervalued part of astronomy. And you might think like, okay, we've been observing the sky for a really long time. We should have covered all of the sky in every bandpass, at least looked at it one time. And that's actually not true in the ultraviolet. So this is showing different types of light, X-rays, gamma rays, different extreme UV, far UV, near UV. This is Lyman UV, which is just a particular subtype. The visible, near infrared, mid infrared, far infrared, and then radio. And most of these, we have 100% sky coverage, which means that we at least looked everywhere in the sky at least one time. And in the UV, that's not true. We've only covered 70% of the sky. And in this particular sub part of the UV, less than 1% of the sky has been observed. And that's because the UV is like kind of a challenging wavelength to work in. But it also means for me as a scientist that there's a lot of really interesting stuff in these missing percentages where there's like things that we could discover. And I won't get too much into the technical bits, but like part of why the UV is sort of left behind is because, first of all, the atmosphere is challenging, but that's challenging for X-rays too. The materials required for a UV telescope are similar to what would be in an optical telescope. You have mirrors with like surface coatings, but everything that works in the visible starts to break down a little bit as you go farther and farther into the UV because those photons are so energetic. But unlike X-rays, they're not energetic enough that they'll just like punch through everything. So they tend to get trapped easily. They'll get absorbed. Over time, they'll actually damage whatever the thing is made out of. So it's almost as if like, well, I live in Tucson, it gets really hot in the summer. If you leave a piece of plastic out in the sun, it'll get all brittle and crumbly. And that's actually the damage from UV photons. So the UV will slowly destroy whatever you're trying to observe. Also because it's not really useful on the surface of the earth, there isn't the same like military or commercial or ground-based kind of applications to drive some technology. So I think those things combine to make it just a little bit harder than other wavelengths. The infrared, for example, has a tremendous amount of investment from military sources because you can use that for like night vision goggles and a bunch of other remote sensing. And the infrared is useful in all sorts of diagnostic capacities. But the universe is actually mostly in ultraviolet is one of the things that I say. The ultraviolet is tracing some of the most energetic things that happen in the universe. You're looking at like the births of stars and the deaths of stars. You're looking at where hydrogen is out in the universe. It's really like this key tracer of a lot of different processes. So this is an example of a galaxy that was imaged in the visible on the left and then in the ultraviolet on the right. And they look similar, like both of them look like spiral galaxies because it's the same galaxy. But the ultraviolet, you have a much greater contrast between the spiral arms and then kind of the in-between places. Whereas here, this is more like diffuse glow. The ultraviolet is actually tracing where new stars have formed. And so you're looking at the newest star forming regions where there's like activity going on. And if you look at kind of over here in this arm, it's super bright in the UV. There's a lot of action happening. Whereas if you look here in the visible, it doesn't look necessarily that different than other parts of the galaxy. The other thing is like this galaxy has almost no new star formation at its center. The color here is all red colored. So there's not, that indicates that they're older galaxies. Whereas again, in the center, if you're looking in the visible, it just looks the same as everywhere else. So this is part of that diagnostic power that the UV gives you. This is another example of actually looking across several wavelengths at a galaxy and how that can give you different pieces of information about what is happening in the galaxy. So in the middle, we have visible light. And then to the left is infrared. The infrared is interesting because it's almost the inverse of what the ultraviolet is showing. The infrared is tracking dust, like little, mostly carbon silicon dust grains in the galaxy. And then those typically are in places that are different from where stars are forming. So the UV is still tracing the bright star formation. And then you have things like the radio, which is tracing where hydrogen is. And then the X-ray is tracing like the remnants of exploding stars. So the X-ray is not exactly coincident with the center of the galaxy, although it's very close. Usually that is an indicator of the black hole at the center of the galaxy. And then this is another example of how looking at galaxies, you can have you get different pieces of information by looking at the UV. So this is two galaxies which are close to each other in like actual space. And in invisible light, they look like similar brightness. Obviously, they're very different. This is like a satellite of the larger galaxy. But you wouldn't necessarily think that there was anything like too unusual happening. Maybe you have some star formation here in these little pockets where there's like kind of purple. But if you look in UV, this little galaxy is like creating stars like crazy. Like it is so much brighter in the ultraviolet than the primary galaxy. But if you just look in the visible, you would never know that. The picture on the right, bottom right, is just an adjusted level. So you can actually see some of the detail in this galaxy. And what's interesting is that even the shape of it is a little bit different than the shape in the visible. So there's some extra star formation that's happening kind of at the fringes of the galaxy that you wouldn't pick up if you just looked at it in visible light. But you might also be like, okay, galaxies are bright in the UV, like great. What does that do for me? So I'm going to move things a little bit closer to home to the biggest planet in our solar system, which is Jupiter. And one thing that's, I think, very incredible is that we have a lot of UV observations of objects within our solar system. So when NASA is sending probes to like Jupiter or Saturn, there's always some type of UV instrument on it, a spectrograph and imager. And this is just to give you a sense of how different wavelengths, again, are going to give you a different view of what's happening, but this time for a planet. So Jupiter is a gas giant. It's massive. It's mostly made out of hydrogen, and it has these beautiful stripes on it. Basically, the wind at the surface of the planet, and it's driven by the rotation of the planet, the same way that wind on the Earth is driven by the Earth's rotation. And if you're looking at the infrared, you're actually looking at a slightly different layers into the planet. So different cloud tops are different temperatures. And so you can see like these very kind of disturbed clouds are going to be hotter. They'll be brighter in the infrared than the ones directly below it. If you look here, you wouldn't necessarily know that, but the like cloud layers are actually different heights and different kind of levels of activity. And then the red spot is cold. That's why it's dark. If you look in the ultraviolet, you're actually probing like a higher layer in the atmosphere of Jupiter, so you can get some more detail on some of these like fluffier, higher clouds, and a little more kind of focus on certain of these hurricanes that are happening. Another thing which is really cool is that you can look for auroras in the UV around planets. An aurora is when the planet has a magnetic field. The sun is sending charged particles off, that's called the solar wind. Those charged particles get funneled into the poles of the planet along the magnetic field lines, and they make these beautiful auroras. On Earth, we have the aurora borealis in the northern hemisphere, and then the aurora australis in the southern hemisphere. And this is exactly the same process. And you can see like the auroras are active and they change, and they're best observed in the ultraviolet. So this little image was taken with data from the Hubble Space Telescope that was collected over several hours. And you can see how the aurora is changing. The planet is also rotating. One thing about auroras, which is really exciting for trying to find life on other planets, is that we think that a planet magnetic field is required for life. That's to protect the atmosphere of the planet. If you don't have a magnetic field, all these particles would just hit the planet and basically destroy the atmosphere. So if there's a magnetic field, there should be an aurora. And if you can build, there's been a couple of different ideas of like how to build a telescope that could look at planets around other stars and determine whether or not they have auroras, because that would be like a really slam dunk case for proving that a planet not just has an atmosphere, but has a magnetic field that will protect that atmosphere. And then moving on to the sun.
Oh, Dr. Hamden, I think we've lost your sound.
It's just the TVs, they take some time every so often.
Okay.
Oh, can you hear me?
We can hear you now, yes.
Okay. So then moving on to the sun, we have a telescope that's actually in orbit around the sun called SOHO that has many different UV channels. And the sun is a really great example of how active and interesting stars can be in the ultraviolet compared to what they're doing in the visible. So this image here in the upper left is the sun just in the middle of the visible band. It's yellow, kind of like it is when you look at it on Earth. And you can see some sunspots here just in this little clump. And then these are different wavelengths in the ultraviolet as you move across and then down, as this number 1600 angstroms, 305, 171, and so on. As these get smaller, you're looking at a shorter and shorter wavelength, more and more energetic photons. And all of these other images are in the UV. You can see that the 1600 angstrom one doesn't look that different, actually. It's like sort of an inverse. But what you're looking at is the upper photosphere. So you're moving from like the surface of the sun and then moving outwards. So you're actually using the wavelength to kind of measure different layers in the exterior of the sun. So as you move to shorter wavelengths, more energy, you'll notice that these temperatures get higher. It goes from 6,000 Kelvin at the surface of the sun to 6 million Kelvin in the like inner corona of the sun. And you don't really start to pick up this region, even though it's called the quiet corona, is where you actually see most of the magnetic field lines, and a lot of the magnetic activity of the sun is best traced in this wavelength. So looking at all these other wavelengths, it gives you a more three-dimensional picture of what's actually happening in the sun. And then I thought this picture was just really fun. So this is the sun being transited by Venus. So this is the Venus transit. And this is a composite image of 3 different UV wavelengths and that are combined together to just give you this view of a really dynamic and interesting star where a lot of magnetic field activity is happening. There's coronal mass ejections. There's like a continuous churning. And that's the kind of level of activity that if you're just looking at this happy yellow image, you're not necessarily going to see it. And so to kind of go back to my beginning point about how some parts of the sky we don't even have UV data for, these 2 images, this is a visible wavelength and then an infrared wavelength image of Orion or the Orion Nebula. And we do not have an ultraviolet image that could go next to this set the way that I showed the sets of like Jupiter or galaxies. Partly because for technology reasons, the brightest, most interesting things in the sky we have not looked at in the ultraviolet because the detector technology that we use just can't, it'll basically get saturated. So you can't look at really bright things, which is a shame because this is a really interesting active star forming region. It's one of the regions closest to us. There's these like huge new stars that have formed and we don't have a full picture of what's actually happening with it because we can't look at it in the UV. Then there's some other, like, I think really important science that can be done in the ultraviolet. So we've started looking for planets around other stars. We're finding a lot of them. It's like above 5,000 now, but we're really looking for an Earth-like planet around another star, ideally a sun-like star, but a planet where we think it can have life. And looking in the UV is really important to figure out whether there can actually be life. So not just looking for auroras or the magnetic field, but the actual level of activity around that the star is going through is mostly, so some stars, a lot of stars actually are highly variable. They'll get brighter and then dimmer and then brighter and then dimmer. And that will change the atmosphere of a planet, even if that atmosphere is protected by a magnetic field. So knowing the like UV activity of the star can tell you whether it's worth investigating the planet. There are certain types of stars which could be really good hosts for planets that are like Earth, but they're way more active than the sun. And every 100 years or so, they just like send out so many photons that it would irradiate the planet. Even if there's a magnetic field, they just like have these huge flares that would overwhelm any protection that the planet has. And if you're looking for life, you want to know that the star irradiates the planet every 100 years. It's not going to be a good candidate for life. And even looking at like the atmosphere of the Earth around the sun, there's significant differences. This is again due to the oxygen in the Earth's upper atmosphere. And then this is sort of my this is a very niche thing, but so one of the coolest things that has happened in the last like decade is the discovery that we can measure gravitational waves from things like black holes merging or neutron stars merging. And so in 2017 was the first neutron star merger. A neutron star is basically the dead core of a really massive star. Neutron stars are held up, they're basically giant neutrons. So they're held up by the same force that keeps a nucleus together. but they can only be up to a certain mass. If they get higher than that, then they can't hold themselves up and they collapse and there's this huge explosion. So if two of them merge and hit each other, there's like a really huge explosion. And you can measure the gravitational wave effect, like the effect that that merger has on space-time, and then you can also measure the light that comes out of that explosion. And the light is brightest at the beginning in the ultraviolet. So this is a figure from the actual discovery paper. And the two UV telescopes here didn't get to look at it until a couple of days after. So Swift is a UV telescope, and then the Hubble Space Telescope has a UV channel. It didn't get there until 5.5 days later. But if we had observed it right at the merger, it would be really bright in the UV, which is over here. And then over time, it cools off over the course of even like a week. It cools off, and then the peak moves into the visible and then into the infrared. So having the ability to follow up on these really incredible events in the ultraviolet is, I think, going to be very important for future work. So I'm going to just talk a little bit about my own scientific interests in the time that we have left, which are all related to observations in the UV. And for me, I'm concerned with like, what's up with galaxies? I showed a lot of galaxies earlier because I really like them. And what I want to know is like, why do galaxies look the way that they do? This is an example of kind of like a rogues gallery of galaxies, and they have all types of shapes and sizes and colors. And we don't really have a good explanation for why. Some of them we can be like, oh, there's a merger happening. Two galaxies are close together and they're going to merge, and that's why they look the way they do. But a lot of them, we don't have that clear picture. And one of the links, I think, is how galaxies interact with their environments. We see the galaxy in the visible as just this like little clump in the interior here. So this, in this like artist representation, this is the galaxy. But the galaxy actually sits in this much bigger halo, is how we refer to it, which is full of hydrogen. Material gets thrown out of the galaxy from a supernova explosion. It comes into the galaxy as in these big flows, and it's this like really active and interesting environment. The effect of this is that the environment of the galaxy can both change how it looks, and it can also change whether it's able to make stars or not. So way at the beginning of this, I showed you a galaxy where there was lots of new stars on the outside, but no new stars in the inside of the galaxy. And there's this like change in star formation rate in the universe overall. So the universe formed 13 billion years ago. This plot is a little technical, so I apologize. 13 billion years ago is like here. And then for the first couple of billion years, the rate of star formation increased and had this peak like 10 billion years ago. But since 10 billion years, the rate of star formation in the universe has been declining. So we live in this like era of declining star formation, which is kind of, personally, I view it as a bummer. And so one of the things that I want to do in my scientific work is try to understand like, how does this, how do we explain this era of declining star formation by actually observing not just the individual like galaxies, but everything around the galaxy, the entire galaxy halo. So two of my projects are sort of focused on looking not at the galaxy, but the stuff that's around the galaxy. And I don't have time to get into too many specifics, but so the first one is called Fireball, which stands for the Faint Intergalactic Medium Redshifted Emission Balloon. This is a pretty big collaboration between Caltech, a couple other places in the US, the University of Arizona, and some team members in France. We've flown the telescope in 2018 and 2023, and balloon telescopes are weird. I could give a whole other talk about balloon telescopes. So the telescope is actually hanging right here. This is the balloon when it comes off the ground, and as it ascends into the stratosphere, it'll get bigger. And we launched them from Fort Sumner, New Mexico, which is kind of in the middle of nowhere. Santa Fe is over here. Albuquerque is like over here in this graphic. And this is me, I'm cleaning the telescope mirror. This was a few years ago when I used to run the project, and when you're the boss, you have to do all the things that nobody else wants to do. And so I have a little video of the 2018 launch. We did launch in 2023, but I haven't gone through all of the videos that we made. But so the balloon launches are really fun. They need really good weather. It needs to be really still on the ground. The balloons are filled with helium, and it takes about an hour to fill it up. And then once it's filled, the wind is good, they release it, and everything, the balloon starts to head up. The telescope itself is on a crane that drives around. The crane is called Big Bill. The crane keeps everything lined up so that when the balloon is fully vertical, they can release the telescope and it'll all just like gently float away. And we operate out of this municipal airport in the town that's pretty empty. You can see there's not a lot around the airport, and that's on purpose because in case something goes wrong, you don't want to drop a telescope on somebody's house. That would be that would not be great. And so this was like a really nice, gentle launch. We had a pretty good launch in 2023 as well. It takes a couple hours for the telescopes to get up to the stratosphere. And again, we're going there because we want to be above most of the atmosphere. You can see this is a GoPro that's looking up from the bottom of the telescope, and you can see the balloon at the top of this video. And then this is once it's in the stratosphere. So I know Dr. Parks already said this, but the Earth is round. We have the proof. And then this is what we open the doors to do the observations. You can see the balloon is way bigger. And then this is after the fact. Both the balloon and the payload get cut down. There's a parachute, and then you go and find the telescope. It lands in somebody's field, and you like ask them nicely if you can pick it up. And then this is a picture that was actually taken in 2018 of the telescope and our balloon. So the telescope is this like little clump of pixels right here. And it was just by coincidence that someone with a good camera actually took a picture of it, and someone else found it on the internet and sent it to me. So Fireball is one project that is trying to observe these galaxies in the ultraviolet. And then another project, which again, I won't get into too much detail, is called Aspera. So Aspera is the Latin word for difficulty. We took the name from this saying, ad astra per aspera, to the stars through difficulty, because with this project, we're trying to make a really hard observation of not the galaxy itself, but the stuff around the galaxy. So this figure is a simulation. The galaxy itself has been removed from the center just for the scaling, but we're looking for oxygen, like oxygen atoms in the halos of these galaxies. So this is a huge simulation. We're talking, like this bar here is 12,000 light years across. So we're looking at a galaxy in this like big environment. And the simulations tell us that there's these big filaments of oxygen that are feeding into the galaxy. And what we basically want to do is be able to detect that oxygen directly. And so it's a really hard measurement because we're looking for photons that are emitted from oxygen atoms at these things that are millions of light years away. We have a list of targets that it's about they're all like relatively nearby, but they're still pretty far. And the idea is we'll be able to sort of map this whole region and see if it actually looks like what we think it should look like, which is the simulation, or if somehow it looks different or not at all what we think it will be. And the Aspera project is also really fun because we're doing the entire thing at the University of Arizona. We're building the instrument, we're doing all the mission management, we're doing the software. The only thing that we're getting from somewhere else is we purchased a spacecraft, which you can just purchase. But this is also nice because it's a really good student project. And so this is the size of the telescope. So you can see like a person here holding it, one of the grad students. And it's really great because this project and also Fireball are really good for training students. We have undergrads that work on it. We have graduate students that are working on it. A lot of bigger telescopes like JWST, you have to be like a professional engineer to be, even be able to like screw something in. And smaller missions like the ones that I've worked on are really great because they give students the opportunity to have hands-on like action in something that is going to go to space. So that's one of the things that I really love the most about it. So I'm going to end here to make sure that there's time for questions. But thank you so much for having me.
Thank you. Are there any questions for Dr.? Well, I'm going to start off by asking, why are the lambda photon or Lyman photons so neglected? like, I saw that you were talking about the sky coverage, and there, even with the other ranges of UV, those are at least 70%. Why is it that little band is so neglected?
So let me bring up that, I can bring up that slide. It's, yeah, so this Lyman UV band, where there's a lot of really interesting emission, is so neglected because it is the hardest from a like materials standpoint. So in the visible, if you're building a telescope, you have a mirror with an aluminum surface. The aluminum is what gives it the mirror-like effect. In the near UV and the far UV, you can have aluminum with different overcoats that protect the aluminum surface. In the Lyman UV, you can't use aluminum anymore. It doesn't work. You have to use like silicon carbide or these other substances that are much more difficult to work with, and the performance is very bad, even if you do get it to work. So that's the issue for the mirrors, but that's also true for the like detectors for any dispersive elements. So the building it is so hard that you have to like basically, and then the other thing is, in order to build these telescopes, you have to convince NASA or like the European Space Agency, you have to convince a funding source that it's worth doing. And partly because it's so challenging, the people that could build telescopes for this wavelength range are like, well, I'll do something that's slightly easier in the far UV or slightly easier in the visible. And like it just sort of like drives people away. But I feel like, I mean, the fact that it's less than 1%, like there's so many things to discover in this. So someone who is willing to put in the effort to make this telescope, you are going to discover a whole lot of stuff. So actually Aspera, the telescope that I talked about at the end, is in this region in the Lyman UV. It's like right in the middle. And so partly just because nobody else has looked there, I think we're going to discover a lot of really cool things.
Good job.
Yeah.
Anyone else have a question? Yes,
I have two questions. Is that okay?
sure.
You mentioned like it was like coronal sunspots. Whatever. Could you talk about like what that is?
Yeah, so let me bring up the picture of the sun. So when we look at the sun through a telescope, you obviously need to have a bunch of protection on the telescope to make sure you don't melt it. The sun has a lot of photons. If you're looking invisible, you're looking at what we refer to as the surface of the sun. It doesn't really have a surface because it's a plasma, but you could also call it the photosphere. And you're viewing, basically, this is the point in the sun where photons stop hitting molecules and just start like moving outward in a pretty straight way.
You've lost your sound, Dr.
Oh, can you hear me? Can you hear me?
And I think now you're back.
Okay, that's so weird.
Yeah.
I apologize.
No.
So
On our end, no worries.
the photosphere gives you a not a really good view into what is actually happening in the sun. So the sun is fusing hydrogen into helium in its very core, which is pretty deep within, but then there's like different layers and
We've lost sound again.
Oh.
How do I get to these two speakers? We always seem to have tech issues in this room. I do apologize.
That's okay.
Well, we have you now, so.
So the sun is fusing hydrogen into helium at its core, but it's also rotating, and the rotation is not even. And because it's a plasma and it's rotating, it creates this magnetic field, just like the Earth has a magnetic field, Jupiter has a magnetic field, the sun has a magnetic field. The sun's magnetic field is like a big old mess. The Earth's, you can sort of approximate as like a bar magnet, but the sun's is continuously getting twisted up as the sun is rotating. The center part rotates faster than the poles. And so because of that, you get these weird effects. So like you can see here, this is a pretty classic magnetic field loop over here. But each of these kind of discontinuities or like bright spots or dark spots is evidence of magnetic activity. And the sun goes through these 11-year cycles where it'll become very active. You have a lot of sunspots. The magnetic field is really twisted up. If the magnetic field lines break, like here, for example, which does happen as they get twisted, the gas from the sun that is like here and here will get blown out into space. And that's called a coronal mass ejection, because part of the corona of the sun is getting sent out into space. That can actually cause auroras on the Earth. If they're really bad, they can interfere with satellites and communication systems that maybe aren't as protected by the magnetic field. It sort of like shrinks the Earth's magnetic field temporarily. So looking at the sun when it's really active, you'll see something that looks like this, where there's just like so much going on. There's all these like twisted regions where the magnetic field lines are coming in and out of the surface. Versus if it's a really quiet time on the sun, it'll look more like this image or this image where there's really not a lot happening. I don't know if that answered your question.
Yeah, that did. And then.
Yeah, the second question?
Yeah, my second question was, I don't know if this is a good question, but how are UV rays made? Like, why is it more energetic?
So let's see if I have a.
All questions are good questions.
Yeah, all questions are good questions. Your question is actually like really hard to answer. So okay, so any photon is just a different form of energy. So you can have energy, like your body is a certain body temperature, and then that energy will get released as photons because of the temperature of your body, and they'll be infrared photons, and they have like the energy that sort of corresponds to the temperature of your body. For the UV, it's coming out of a more energetic object. So something like a really bright star has a temperature of like 10,000 degrees. And so those photons will have more energy because the like part of what is making them is hotter and more energetic overall. That's like not as precise of an answer as I would like, but when the sun, for example, it fuses hydrogen into helium, that process creates a little bit of energy, and that energy comes out in a gamma ray in the core of the sun. But then over time, so the gamma ray can't immediately leave the sun because there's too much stuff in between. So it will be emitted, and then it immediately hits an atom, gets absorbed by the atom, and then gets re-emitted, and it'll like slowly make its way out of the sun. And over that process, these like sort of atomic level processes can take a gamma ray, which is very energetic, and turn it into many UV photons or many visible photons. It'll like change, you can change the wavelength. You're almost like splitting it up into several different photons. The combined ensemble will have the same energy as the gamma ray, but it gets split up into all these different photons. And there's other ways that you can like add energy to a photon. A lot of it has to go, you need like an atom to kind of mediate the process. But you're asking a really deep quantum mechanical question, so it's not a silly question at all.
Sure, yeah.
Sorry.
You have a follow-up?
I don't know if we already have, but, or if like theoretically, if we could like create UV rays ourselves, like add energy to it, just like how we're able to like heat things up and create our own artificial light.
So there's certain, so like we have some UV sources that we could use like in the lab, for example, where you take certain elements and you heat them up really hot, and then they'll preferentially emit UV photons. And it's a different process. So like we can create X-ray photons, like what are used for dental X-rays or medical X-rays. And that's actually a different process than how you make UV photons. So depending on what wavelength you want, you would use like a slightly different, there's like certain materials or certain processes that you're trying to like get the atom to do in order to get the wavelength of light that you want. But light, I mean, those questions are all really good. Light is like a really weird, mysterious thing.
Very much take for granted.
Yes, and we really need it.
Any other questions? Yeah,
So could you go back to the slide of the sun real quick?
like a really pretty picture of the sun.
The one with the different wavelengths and temperatures. Yeah, so my question is that kind of going down from 4,500 to 171 angstroms, you seem to be going up in temperature, but then 304 to 335, you go from 50,000 Kelvin to 2.5 million. So what's the relationship between the wavelength and the temperature there?
So this is a good question. So the sun has this weird effect, which we don't understand, which is that the surface of the sun is cooler than the atmosphere around it. There's this like strange temperature inversion. And so the photons, I just said like you can make the photons if you have a certain amount of energy. But in this instance, you're seeing photons that are coming from they're coming from the sun and they're passing through these regions. And so the temperature of the region that it's like, how do I want to phrase this? The temperature, for example, in this 94 angstrom image, is hot enough that it changes the atoms that are at this kind of layer, and those atoms then interact specifically with this wavelength of UV photons to give this kind of imprint. So it's partly the temperature of the material and then where the UV photons are coming from and how they like interact with material of that temperature. The fact that this temperature keeps going up is something that we don't actually know why.
You have questions, sir?
Yeah, it was about the unobserved area in the spectrum. What do you think we could find in that area, since we have such a small percent that we only know?
So this region actually, man, there's like so many good things in this region. A lot of it is like not flashy stuff. So the most abundant atom in the universe is hydrogen, which was formed in the Big Bang in these tremendous amounts. Hydrogen, if it's even slightly dense, will bond with itself to form molecular hydrogen, two hydrogen atoms that are bonded together. We think that molecular hydrogen is the precursor to all stars, that you need your hydrogen to condense and get denser. It forms molecular hydrogen and it gets denser. Gravity causes things to get denser, and then you have stars that form in those dense regions. Molecular hydrogen emits a really beautiful spectrum in the Lyman UV. It also does in the far UV, but there's more and brighter lines in the Lyman UV. And so if you wanted to take a census of molecular hydrogen, like in our galaxy, you should look in the Lyman UV and the far UV to see where it's actually emitting. The emission is from fluorescence, so it gets hit by a photon. It doesn't break apart, but it sort of will start to vibrate because it's just like two symmetric atoms, and that vibration will emit a bunch of photons in this very characteristic spectrum. And we don't actually know, like a lot of the stories that we say about how stars form, like we know that stars form where there is dense molecular gas, but we don't actually know if it's required. Like in the early universe, was there dense molecular gas, or did stars just form out of hydrogen, like straight up? And part of the reason why we don't know a lot of that process is because we're not looking at the molecular hydrogen itself. We're looking at other tracers that are easier to observe because they're like in the near infrared, but they don't give you the precise information of like how much material is actually here to go into the star. So for me personally, that's like the most exciting thing about the Lyman UV. There's also a lot of higher atomic emission lines that have signatures in this region. So Aspera is looking at oxygen emission, but there are other atoms that we could look for in the halos of galaxies, silicon, neon, carbon, a lot of those are actually emitted in this wavelength range, and we can observe them in more distant galaxies where the light has been redshifted into an easier bandpass, but for the galaxies like right around us, we have no idea what they're doing in this wavelength range.
All right, well, I think I'll ask the last question, which is, where do you get all of your fabulous glasses? I love your glasses.
Good question. I have some from Warby Parker. I recently ordered a bunch from Zenni Optical, which they sell glasses for like $28, which includes the lenses.
Yeah.
And so I like last year I got like 6 different pairs of glasses and I switched them out based on my outfit.
Thank you. I will definitely be checking that out. All right, if we could have another round of applause. For doing this. And now we're going to, Seer and Jonathan are going to split you up into groups and take you up the elevator to our observatory.
Thank you. Have a great time on the tour.
Thank you. Thank you again.
I think we can split ourselves off into 2 groups. I'll go ahead and start